I'm Carlos, and I work in the Max Planck of Light in Erlangen, Germany. And I work for Mario Kren in the so-called Artificial Scientist Lab. Today, I will introduce PyTheus, which is a Python library for the automated discovery of quantum optics experiments. It's probably one of the largest projects we've done so far, and it's very representative of like the general goal of the group, which is like use computers to like make new devices and new experimental proposals. Let's start the talk with like a small thought experiment. Let's imagine the universe, but the universe of quantum optics experiments, and in which every of these stars will be like something useful that you can do with the standard tools that are available now, like lasers, mirrors, beam splitters, these kind of devices. Humans will have achieved with the available resources and combining them in clever ways, like some of the like successful tools we have now, like telescope, microscopes, and also all kinds of communication systems and even like quantum computers. And what we try to do is just go beyond that, go to the and find new ways of using the same tools that we already know to get something new from it. Here you also see, and it's not an accident, that there is like an overlap between the two. One could think that rediscovery is not so like fascinating, but it's actually what gives us like some ground. So when we are developing a new algorithm to find new solutions, it's always nice to see that it's also able to recover some of the previous ones we know work well. And, and to do this, to navigate through this space of experiments in a similar way than like basically like Midjourney can navigate through the space of potential images and give me this one in particular, we go through three main steps. The first one is to represent the physical system that we are interested in and the properties that we want to know from it. We may not need every detail of the system. If you're like with the example of the molecule, we will not require to know where every atom is located, but rather like some simplification will probably suffice for many of applications. Even like an abstract one that maybe for humans is not so straightforward as this string here, but the computer will still be able to manage properly. The second part is the exploration. And for that, you need to set a very clear target that you can encode and give to the computer. You can ask to predict properties of the system that you're looking at. You can ask how to enhance certain properties, doing transformations that you can act on the system. And finally, once you get a novel solution, we will not be happy just to have like a magic oracle telling us how to do science. But actually what we are looking for is to understand what we are getting. And by that, we mean that we are not only able to use the particular solution, but also extrapolate the underlying principles to new ones and explore like bigger systems with the insights we got from these small ones. I like this example of the molecules, and also Mario used to work on them, so I don't know, it feels close. But actually, we do not work with molecules, we work with quantum optics experiments, which, for those who are not familiar, are like a very promising platform for quantum computing. Also, they have applications in quantum imaging. And I think one of the most well-established applications so far is quantum communications. I will explain in a moment, for those who are not so familiar with like quantum mechanics, some of the properties that makes quantum light a useful resource. But before that, and even before I start explaining how PyTheus works, I want to set the big picture and show you the beginning of the whole process project, which was melding. Melding was an idea that Mario had in 2016, maybe a bit earlier, which was, okay, I'm not finding the experiment I want, so why I didn't get the computer made it for me. And to achieve that, he digitalized the main tools that you can find in the lab and how they interact. And then he just established some basic algorithm in which the pieces were combined to produce a new experiment. Once you have the experiment, you need to check that it more or less makes sense that it's just not random stuff put together, that there's no lasers pointing to each other or to your eyes or some other security checks. And if the experiment makes sense, you go and compute which is the final state that you're getting, or which is the final transformation, and then you evaluate how close is that to whatever you were looking for. And if it's good enough, you report the solution, and if possible, try to simplify it further. But not only the full experiment. You also go to individual parts of your experiment and try to see if like that particular subset can act as a piece that you can use in a new setup, because it's making like some new function which it can be exploited somewhere else. Then you can add that to the toolbox and iterate on this loop. This trick of simplification and adding the new devices was actually like a key part of getting new designs, and it led to the discovery of a higher, like basically a system that was able to create GZ states, which are like entangled party states between many parties beyond qubits. Again, I will explain in a second what entanglement is and more. But let me highlight one of the problems that this approach has, which is that you are exploring a discrete and infinite space. You are like setting independent pieces like as if they were like Lego, and you actually don't have a limit of how many you can put, and there is like a lot of redundancy. So this is kind of an computational nightmare. So to go beyond this problem, Marriott like developed a more abstract representation of these same experiments, which is the path identity. In the path identity, you don't care about the details of how the photon is reaching the detector. You don't care about which particular mirrors it bounced back or which beam splitter it crossed. You only care about the kind of sources that you have, like the kind of photons that are created, usually in nonlinear crystals, which are just like a crystal in which you pump a laser and then you get 2 photons out of it, and where they end up. So basically, to which detectors the photons go. You can have them in different quantum states, 0, 1. If you're dealing with photons, you can encode that in linear polarization, but not only. That is just one example. And for those who have heard of superposition and are familiar with, by the way, you can also have like the photons to be like in 2 different states. Forgot that. Going back to the superposition, if you're familiar with photons and how linear polarization works, superposition is just like a different basis of the same Hilbert space. So you're just splitting the same 2-dimensional space in a different way. The funny part of this is that if you're standing in states like the +1 or the minus, and you try to measure and know whether it was on 0 or 1, so you choose the wrong basis, you will project the state that you had into a new one, so you will destroy the information available, and that is exploited in several communication systems to establish it between parties. So it's a very useful resource. Let's go back to the crystals, and let's add one more. Here we have 2 and 4 detectors and a laser pump, which can, if it's powerful enough, produce either a pair of photons in one of them randomly, or also like produce a pair in each of the crystals. So you have 4 photons in total. In the experiments I'm going to show you, in general, we assume that every detector is reached by exactly 1 photon. In practice, when we are doing the experiment, you will have like situations in which you generate less or more, but we will filter out those. So now we have this setup, we have 4 photons. Let's combine these crystals in a slightly more interesting way, and let's align them. Now, the overlap on the optical paths means that when the photons reach the detectors, one doesn't know where they came from the blue source, so like they are in 0 mode or in 1. That generates a superposition between the 2, and this is an entangled state between like 2 photons, because you cannot describe this state only by looking at one of the photons, and rather you need to describe some global property of the 2, which in this case would be that the photons are like parallel in terms of polarization. These kind of states can be shared, so you can share a photon with some party, and based on the measurements that you do on that, and establish a key. But I need to stress this very hard. Entanglement does not allow faster than light communication. So if you share like some photons with some friends and try to establish a key. Out of that, you will still have to share information about which measurement you applied on that, and according to that, arrange your key. So you still need the classical communication, not faster than light. So everything's safe. Good. And going a step further, we can add a second, like basically we can duplicate this, which will lead to two subsystems, which are kind of independent. But now we can start playing around, a bit more clever, and rearrange the, the optical paths so that the photons that reach the four detectors are all of them entangled. So now you have an entanglement between four parties, which it's the GHZ states. In this case, only with qubits. This kind of resource can be used to establish secret key sharing between several parties. So it's, in general, like as a rule of thumb, the more parties you have, the more optical levels you have, the more nice things you can do. So that's a thing that we look for a lot. Highly entangled between many particles. Good. This came was followed briefly by the graph representation. So briefly after, they thought, oh, actually, we don't need to even represent these experiments with boxes or detectors. We can go a bit more abstract, and it pays off using graphs. So instead of having the crystals, which are the boxes, you just have edges, which represent sources of bursts of photons going to the detectors, which are the nodes. And the weights of the graphs are the amplitudes of the different creation process. Like, roughly speaking, how likely it is that the different photons are created, roughly speaking. So from this, you map into the final state by the different perfect matchings of the graph. That means the different combinations of edges that cover all nodes. Each of these perfect matchings is a term that creates a quantum state. Here you have only two, as before. It doesn't require to be even. The only thing that you impose is that it's normalized. But you can, I think, already see that you can add very easily a couple more crystals or a couple more edges and generate an additional contribution to, for example, the 1-1-1 state. This additional contribution, if you want, you can make it negative. So you can put a negative amplitude, and then you will make the, the two contributions interfere. If you want, you could cancel that, and then you will only have the 0, 0, 0. It sounds like a very cumbersome and useless way to get the 0, 0 state, because you could just have the blue thing. But actually, some of the more interesting solutions that we have found, and the more counterintuitive, come from clever patterns of cancellation of terms that you didn't look for. I have a big, pretty cool example of this later, which I think it's a bit too much for the topic, but if you are curious about it, I can show it afterwards. Anyway, since this is not really this cancellation is not making anything better, let's use those additional resources for good and add an additional dimension. So with a 4-particle system, you can, without any kind of destructive interference, generate a GHZ state, so this highly entangled state, between 4 qubits. And this is the graph representation. And one of the main advantages that it has compared with Melvin is that now you are in a finite and continuous search space. Once you fix the topology of your system, you only have to optimize the weights to get whatever you're looking for. And that is actually nice. And that was already exploited in some proof of concepts a couple of years ago. But now we have gone one step further with PyTheus by making it much powerful. The workflow, however, remains kind of the same than the previous version. You start with an initial graph in which you describe how many photons you have and which dimensions you have access to. So the colors there. And then you can also add additional constraints if in some situations you don't want certain detectors to be connected because that may represent a communication system between Alice and Bob and they cannot interact directly. Or maybe you have some intuition, some symmetry concern, whatever. You know that you do not need, or even you don't want to have certain edges. And once you have settled your first graph, your initial graph, you can see what it produces and compare it to the target. So let's say a GHZ state, so this highly entangled, with 0, 0, 0, and 1, 1, 1, 1, like 6 of them. So now you have your loss function, which is this fidelity with respect to the generic state that the graph on top is producing, and you can start the optimization process in which you compute the weights. And once you get a solution which it's good enough, you can also start to simplify, to remove some edges, usually the smallest ones, until you cannot simplify your solution any further, and then you get the final setup. This final setup always has at least a naive way back to the optical table. So you can always from this graph design some experiment to produce it. The naive way, it's not super efficient, so you may want to tinker around a bit in order to make it like easier to do, but there is at least one, and that's already very powerful. So with this, we were able to produce more than 100 new experiments. By the time of the paper, it was 100. But now, of course, time has passed. And many of them are actually in the state generation. So we produce states which may be useful for certain tasks in either computing, sensing, or communications. With the new framework, we are able to produce larger systems with more dimensions. Also, in some of them, even like we have a lot of resources, we cannot produce certain states by only using like 4 nodes. Rather, we need to go to use additional ancilla photons to produce it. You can just call this a kind of padding. In an example I will show later, the need of this will be more obvious, but for now, it's just like a technical requirement. So if you see these boxes there, it's just that additional terms that do not matter for the final application, but are required to get them. The other thing we did was changing the rules of the game. Before, I told you that we had a photon per detector, but actually we can also process the whole graph in different ways and compute contributions in which for like a certain number of the detectors, so like in a certain set of optical paths, you don't have one photon in each, but rather you know that in total there is like a certain number, like 5 photons. This is a null state of 5 photons, so you have like 5 photons going in either one of the 2 paths. And this is, and the loops are basically like photon sources in which both of the photons can go through the same optical path. And this is like a whole family of these kind of states, which are used in many senses, I think. Good. Finally, we also expanded the framework to mixed states, which are quantum states in which you do not have the full information of your system. Maybe there was like some noise, some interference with the environment that led some information of the state to be lost. And that it's like those states are still useful and you want to work with them. So here we have one like that in which the environment is like described by this star, which means that the information there has been collapsed. So in the superposition that I showed you before, this one has been collapsed and you don't know what came out from the measurement because maybe it was just like some noise interaction that you didn't know about it. Good. That's on the state generation, but we didn't reach 100 experiments by only doing the state generation, even though we used a lot of them. We also went to information quantum information tasks. So we mapped, to get this, we mapped the creation of certain states to quantum information problems. For example, entanglement swapping. This solution here, it can be split in different parties, which can be Alice, can be Bob, and some intermediate Alice. And what this graph leads to is to a setup in which like the Alice and Bob can share up to 3 entangled pairs of photons that has never interacted before. This kind of entanglement swapping systems are like a very important piece into the scalability of quantum communication networks. Good. The other thing we did was measurements. So we had like certain photons going in, and then the detectors were like actually making a measurement. The triangles indicate that you don't have like that you do not read the edges as single crystals anymore, but rather like a photon going from the in to the out, even though you may not know to which one. And we, with the same principles, we were also able to implement photonic gates that can be applied in photonic quantum computers. For the measurement one, actually, we designed some which were a direct claim from one of our collaborators in Canada, in Ottawa, in particular. They wanted to produce like the minting problem, which is like a puzzle that can only be solved like if you have certain entanglement, and it can be also used for like key sharing. And the interesting thing is that they were able to get this design, also go beyond that, so make generalization for more dimensions, and turn it into an experiment which was simple enough to be like doable. Because as I told you, like, okay, you can always go to the optical table, but the more straightforward, it may not be the more feasible solution. But they found a more feasible solution, and they generalized it beyond what the basically beyond the two particles, which were the only like the previous experiments available for this. Sorry, not two particles, but two dimensions. Good. So this on the measurements, and this is something we already know that it like could be developed, but actually we are very optimistic about further achievements because there's been a huge increase in the so-called integrated photonic circuits, which are just like an optical table in the size of a chip. And that it's a very suited platform for like everything we are doing. Actually, this particular group was also using the representation we developed, well, Mario developed. So I showed you the representation. I showed you how to like actually look for new solutions. So now it's time to check what did we learn from this. The more obvious thing we found in like a lot of experiments, especially when we were looking for families of states or communication systems, is that there is a lot of patterns underlying these solutions. In some of cases, like the patterns like kind of hit us on the face. So this is the decay states, which are like highly entangled in a different way than the GZ states, but are still like useful for certain communication tasks. And we saw immediately that we could actually generalize it pretty easily by just adding ancillas, which added the additional dimension that we require. In some other occasions, for like the so-called W states, for example, which is sharing like a range of qubits in which the only information you have about them is that at least one of them is on an excited state. Well, in this case, we found several solutions for many particles, but it was not so obvious which was the underlying pattern. We had to think around with it until we found that. And now we have a master student who is actually trying to also generalize other experiments, and what he's using to do that is like 3D representations of some of them, because that kind of helps, especially when you have like very integrated with a lot of dimensions. And yeah, he's doing a really nice work with that, a lot of coding, but he has some very cool simulations and animations. So it's very nice. Very good master student. Good. So the second thing we observed is that similarly to what happened with Melvin, we also observed that certain subgraphs act as an independent piece, as an independent tool, like emerging phenomena. For example, in the graph I showed you before, if you wanted to add an additional dimension to that solution, you will not have any perfect matching tree. So there is no combination of edges that you can use to cover all the nodes, which do not use at least one of those edges available there. If you want to add more dimensions, you need to add ancillas. In particular, you need to do something like this. What my colleague figured out was that this thing, like this kind of subgraph, was acting as an independent thing that you could add on top as many times as you want. And it was effectively acting not as a source of two photons, but rather as a source of 4 photons, which has a different behavior on the whole system. So it was not just like you have two sources of 4 photons and they add of 2 photons, sorry, so they end up 4. No. On this graph representation framework, it was actually more like an hypergraph on top, hyperx, sorry, that you could add as many as you want. So if you just close all this system of crystals in a box and you get the triggers, okay, 4 photons from any dimension were created. Oh, by the way, if you wonder how you can encode like more than 2 dimensions on photons, because like, you know, like on the linear space, it's kind of short. there is like different properties you can exploit. You can use orbital angular momentum, or you can even just use like the time. So the time in which you are sending as an indicator of the different quantum modes. And finally, what the whole project led us is that you can actually get very meaningful physical insights from graph theory, which was actually very cool. The solution I showed you before, like for example, like with these 4 nodes, in which you had 3 dimensions, that is not possible, at least not so straightforwardly, for 6 dimensions. If you have graphs with more than 4 nodes, you only have 2 combinations of edges which cover all nodes and are not in any other of these perfect matches. So you have only 2 disjoint perfect matches. If you try to add an additional dimension naively, as you see there, you end up having an additional term that you cannot get rid of. And the best you can do with that is to reduce it asymptotically, but at the price of making the whole event less likely. So basically, you reduce the pump on these 3 sources, and overall, the generation of the state you are looking for becomes far less likely. But the term that you didn't want, the contribution is so small that you can technically integrate. If you want to fully fix this without dirty tricks, you need to add more ancillas. And there is like, as far as we know, there is a proof that you cannot go any better with only real weights. For complex, it's not available yet, but I know that there is like some progress on these things, and part of it also by Alba. And we also had like I'm not sure if you can see the pointer, but the second paper, like we had him on the labs like some months ago, and it was really nice to see that in some points of the world there was like people actually playing around with those graphs and trying to get the solutions from them. It was nice. Good. So we went through the 3 steps I mentioned before. So we're kind of done. But so now let's wonder, okay, what's next? First of all, PyTheus is still like open and growing. Like it's available in GitHub. So if you want to tinker around and suggest new things, you can always do that. We are also looking for better strategies of exploration, because like the workflow I showed you before at the end is just like standard gradient descent. It's pretty straightforward, and we think we can do better. But also, now that you know my methods, you can also apply it to different to new systems, not only to quantum optics. For example, to super resolution microscopy. One of the projects we have so recently with one of the new postdocs is that you can design, in a similar way that Melvin, you can design some setup which is kind of generic. So you add a lot of different sources of light and a lot of different beam splitters and many resources, which are probably like too many, but include some of the solutions that you're looking for. And with that redundant thing, you can already like get some new solutions and then simplify to something simpler. This example is funny because it's like one that we were doing just to check that we were able to find previously discovered solutions. We just wanted very well-focused light, which is useful. And like when you are trying to see small things. And even though we were expecting to get a simpler solution, the one on the left, we ended up seeing these patterns on the SLMs, which are like spatial light modulators. You can consider these spatial light modulators that you see there as some kind of lens that basically like an array of lens in which every pixel is independent from the surroundings. So yeah, a generated lens. And this was actually like slightly better than the previous. So that's why it was found. So the system was working. This is led mainly by our new postdoc, Carla Rodriguez, and Leonard Mako, which is another researcher from the center. Good. So with that, I think I've reached the end. So thank you for your attention. And if you have any further questions about the PyTheus or anything else, yeah, feel free.
Yes, thank you very much, Carlos. So is there any question in the audience? Okay, Alejandro.
Yeah. So I think I didn't quite get what was the effect of the nonlinear crystals, because as far as I knew, the idea was that one photon comes in and two come out, right? But yeah, here I'm seeing there are photons like just one photon going in and one photon coming out. So I'm not
Oh, yeah, that. Yeah, on the original framework, like it was mainly oriented to this kind of nonlinear crystals with two photons. But actually, the point here is that when we are okay, maybe I overdid it with the animations. The point here is that you don't have those crystals anymore. So, when you see those triangles, what you have is either a deterministic single photon source, or some arbitrary input photon that is maybe coming from your quantum circuit and then going down. But if you see the triangles, forget about the nonlinear crystals.
So like in the other drawings or like the squares.
Yes.
Those are nonlinear crystals too, or
yes, those are there. Like yeah, but that was like before the graph representation. So
yes,
the path identity that I showed you was mainly like it had in mind the nonlinear crystals. So yeah, everything that it doesn't include that is after that.
Yes.
First, I just want to thank you for your talk. I am not specialized in quantum computing at all, and I found it very easy to follow. And also was considering talking about optics, which is completely opposite to what I do. So my background is linguistics, and I'm here working at PSC, work on natural language processing technology. And the reason why I'm here is because I had the feeling that this could be useful for language related aspects. And I now I still believe it even strongly, thanks to your presentation. So thanks for that. My question was basically, how possible or feasible do you see to move everything that you're doing with PyTheus into the language, into language graphs? Because I work with some other people, some other universities, and we are having problems with our language graphs, where we try to find insights or characteristics of the networks that are worth sharing or worth comparing with other things. Because we also work with psycholinguistics, and we want to compare with human data in order to model the brain. And we struggle to find out characteristics that connect with what human performance does. Are you familiar with language and how we could use this, or if it has any kind of potential? And if not, would you be willing to discuss this further?
I mean, I'm not very involved in this project, but we have like a project in which we are actually like doing semantic networks, taking like yeah, I promised to summarize the questions, but I will not really know how to summarize your question. So, and the previous one was like whether we were always modeling like only photon per sources. Sorry, I forgot to mention that. But yeah, so going back to your question, like I don't work in anything related to like language, at least not myself, but we have a project in which we go through the literature and try to like make connections between concepts that have not been connected before. So basically like predicting trends in science, and from that also making suggestions of possible collaborations and these kind of things. But for that we use a totally different technology. We use like other tools in machine learning, but nothing to do with this. I'm not sure which will be the targets that you could have on your system. So without that, it's a bit hard.
And one of the 100 experiments that you found could be useful, because we're struggling to find, that how to move forward. Okay, is it okay if I send you an email after this?
Oh, I'm gonna be around for a while, so that.
Okay.
Yeah, over time. Good. So,
Okay. Any other question? I have actually a question. Well, I have a few, but let's see how much time we have. So maybe it's also answering a little bit what he asked for. So all this framework works as long as, and correct me if I'm wrong, you find a graph representation of your experiment or your target.
yes.
And the focus is to play with the perfect matching things.
This one, yes, like most of them, like when one of the solutions I showed you goes a bit beyond that, but in general, that's totally true.
That's what actually my question. So did you generalize it beyond the perfect matching? Because like in the end, I have a super complicated graph and I need to think, okay, how can I map my problem with finding or not finding a particular perfect matching? So my question is, did you move beyond that?
Yeah, so we moved beyond perfect matchings because the perfect matching is just like how we translate into graph language the filter of hey, we have a photon per detector. So that's the condition we impose, and from that you get the perfect matches. If you impose other conditions, like you have a certain number of photons going through a certain number of paths, like in the lunar state, the rules are different, and the kind of terms that you get are not perfect matches anymore. So you get new ones. You wanted to take into account also higher term contributions, because maybe your detectors cannot tell you that only one photon reaches them, but that some photon reaches them. Then you will go for different post-selection rules, which may be like also more expensive to compute. So yeah, they're more like some of them are actually like really expensive.
Any other question?
How is your search in this space? How do you make the proposal? It's random, adding.
Like, okay, you mean, so I start with this initial graph, and so basically, like depending on what I'm looking for, I put more or less resources. So if I'm looking for states in 2 dimensions and 6 particles, the naive strategy will just start with this. Sometimes it's not possible, so you have to like, you run your optimizer for days, you occupy several clusters and you don't get anything. And then you see, okay, maybe I should add more. And then what you add here are those ancillas, which in this case, for example, this ancilla here is the only reason you are able to do this in the first place. And when you are like doing more experiments, and when you're like designing more, at the end, you also get an intuition for the families. You know that, okay, if I want to add more an additional dimension, for example, of this halo thing that I showed you before, the pink thing before, like the patch that was called halo, I forgot to mention it. That thing, you can add it on top once and again. And for that one, you will always like adding a certain number of ancillas. So you get that kind of thing. But worst case scenario, you just put the minimum plus a lot of ancillas and hope for the best. And as long as your computer is able to handle that, you're fine.
And then it runs.
It runs, yes. Yeah, sorry, that's a very important part. Yeah, so you do the edge pruning until you cannot do it anymore. You iterate those two. Yeah. Good.
Any final question? If not, let's thank our speaking again. Thank you very much. Thank you everybody for coming, and I hope to see you again in the next seminars that we organize. Also, if you're interested in any particular topic related with quantum computing somehow, let me know. We will try to find some speakers to talk about it.